day, everyone. Welcome to day 2 of the 3rd annual HPC AI Advisory Council UK conference. Very happy to have you back. We have a great 3.5 hours of speakers and topics. And let's start it off with a little commentary from Mark and Gilad about day 1 and how you're feeling about day 2 coming up.
You want to go first, Gilad?
Well, I started yesterday, so today you need to start.
I'll go first. So yeah, welcome to day 2 then. I'm Mark Wilkinson from the director of the Dirac HPC facility here in the UK. And so this event is being co-hosted by Dirac and the HPC AI Advisory Council. Yesterday, very interesting set of talks and covered a lot of interesting areas around networking and around plans for Exascale in various different communities. And I think, I certainly very much enjoyed all the talks yesterday. I'm looking forward to today where we've got several talks looking at the presentation of large scale compute as a cloud-like presentation and the benefits of that. And then we'll also be hearing about some of the work that's being done by the UK Atomic Energy Authority. So again, looking forward to hearing that as our end note today. So I'll hand over to Gilad, but I wish you all a very good couple of hours listening to these talks.
Yeah, thank you very much, Mark. Welcome, definitely welcome for the second day. I'm Gilad, and for the last 2 days, or yesterday and today, I'm working for Mark, helping to bring this conference, or this virtual conference. Yesterday, there were multiple great talks, and definitely looking forward for the talks today. So not trying to hold. We have lots of presentation todays, and we want to make sure that we run everything on time. Brian, I think our speaker that's going to open the day today is Mr. Paul Calleja. That
is correct.
So if you don't mind, I'll introduce him.
Sure.
Paul,
before you do that, I just want to remind everyone that we are recording the session today. All the slides and the videos of each session will become available on the conference's website as well as YouTube. And we encourage people to ask questions, and you can do that by throwing that in the Q&A. And we're also monitoring chat too. So just in case you're hitting both sides of the house, we're here to help and provide those questions to the speakers who will answer them at the end of the session. Gilad.
Yeah, thanks, Brian. Definitely thanks for the reminder. We do encourage as much as questions, discussions, comments, and so forth. That's the main purpose, actually, for this conference. So if we no further ado, Mr. Paul Calleja, a long time no see.
Yeah.
I hope everything is great on your side, and I'm happy that you're going to provide the keynote, present the keynote of today on Open Exascale Lab. Thank you very much. Thank you very much, Paul.
Thanks, Gilad. Let me share my screen. Are you guys seeing that?
Yes, Paul.
Yes, we do.
Okay, let me go into presentation mode. Okay, here we go. So thanks, Gilad. And I'm on for 45 minutes, correct?
Yeah.
Good. Okay. Just making sure. You have to be careful with academics, otherwise we'll just keep speaking and never stop. Okay. I've got my clock on. It will shock me at 40 minutes. So today I'm going to talk about the Cambridge Open Exascale Lab. This is an industrially funded activity at the university, funded primarily by Dell and Intel. The purpose of the lab is really to drive open technology innovation, to democratize those technologies, make them available to the widest possible audience, and really to implement this design via a co-design partnership methodology. I'll talk about that when we get to that section of the talk. But this co-design partnership, long-standing partnerships with companies like that, Intel, NVIDIA, Mellanox, is a really key to our success and how we work. So the talk is really going to be split up into 3 sections. Just an introduction to the university, just in case you don't know the University of Cambridge. A little bit of an introduction to the computing service and what we do. Then I'm going to segue into just a little talk about the kind of rising importance of HPC as an essential national infrastructure. Of course, we here know this, otherwise we wouldn't be here, but it now is kind of seeping in to the psyche of governments and funders that HPC really is essential now as a national tool, and we'll talk about that a little bit. And then we'll finish on the Open Exascale Lab. So, the University of Cambridge is a kind of a world-leading teaching and research establishment. I would say more focused on research than teaching. There are 70 academic faculties across the university with more than 140 different centres, research-centric activities, 1,500 academics, 3,500 contract research staff, around 4,000 PhD students. So you can see that the research staff and the PhD students really add up to 7,500 people employed at the university directly engaged in research. The university turns over around 1.4 billion a year. Well over half of that is research focused. So a research economy of around £700 million a year. So it's quite a large research economy. Okay. If you look outside of the university, within a 5-mile radius, we have a very active technology cluster. So there are around 1,500 technology-based companies in the Cambridge metropolitan area, employing 57,000 people and turning over another 13 billion of revenue. So in total, you can see that the Cambridge technology ecosystem is really rich. And my division's mandate is to project services to the university, to the Cambridge Tech region, and to the wider national research communities of the UK. So there's been a long history of HPC activity at the university, starting way back really in the 40s with quite a seminal system called EDSAC, created by Maurice Wilkes. This was the interesting fact about this machine was its memory, its load store memory, which was actually a vat of mercury. And you can see those guys peering into that vat of mercury there, highly toxic system. And I think that building is still standing and it's still polluted by mercury, among other things. Cambridge has lots of heavily polluted buildings, of course, the various labs that have been operating for the last 200 years or so. If we roll forward, I joined the university in 2006, and we deployed our first large-scale commodity cluster. Up until that time, HPC systems in the university had been proprietary, what I would call old-fashioned proprietary systems from Fujitsu or Cray or whatever. This was the first large-scale commodity system in the UK. That was actually the fastest academic supercomputer in the UK with a blistering 18 teraflops, which Gilad could now provide me on half of one of his partner's cards. Yeah, it's quite interesting. In 2006, 18 teraflops was 30 cabinets and 200 kilowatts. And today that's half an NVIDIA card. And today we went forward, we've got our new system. It's a cloud-based system called Cumulus. And that has a combined performance of around 10 petaflops. I'll go into more detail. So a long history of HPC at the university and providing HPC services to engineers and scientists. We'll just go for a few key characteristics of the service, just for context. As I said in the previous slide, we've been providing leading UK supercomputing services for the last 15 years at the university in its current form. We launched with the fastest system in the UK back in 2006. Actually, that was number 20 in the top 500 on a budget of just £2 million. Again, that tells an interesting story. £2 million now would get you about position 1002 in the list. It certainly wouldn't get you anywhere near the top 500. It shows you the scale of investment, growth in investment in HPC has been dramatic over the last 15 years. And today, we still have the fastest system in the UK. We've had that position for the last 3 years. Another characteristic of the Cambridge service, I think, is we have a very fast time to solution with new technologies. We're very agile in the way we design and deploy technology. So we do multiple small drops of technology refresh, which over time leads to a much more agile system deployment methodology. And because of our business model, we have very competitive CapEx and OpEx costs per flop. We run as a cost center. We resell services. And any of you that are unfortunate enough to have to sell things to real customers know that you can talk about value until you're blue in the face, but most people just want it cheap. They want it good as well, but they want it cheap. So value is an important part of our business model. We serve one of the largest cross-domain user communities in the UK. This is quite a unique feature of our service. We have a very broad range of users from the STFC, EPSERC, BBSRC, MRC. So obviously the traditional engineering, astronomy, physics, chemistry users, those kind of long-standing traditional HPC users. But actually our fastest growing user community is clinical medicine and biology. So we have a strong focus now on how do you project HPC services into the clinic, into medical use cases. And I think Cambridge has kind of pioneered the use of large-scale commodity systems as national infrastructure. This is normal today. It wasn't 15 years ago. Most large-scale systems then were still proprietary systems. That's mostly fallen away now. We provide these systems, as I said, by a co-design methodology where we have long-standing partners, technology partners, and we co-design shared risk, shared gain, as opposed to a traditional kind of RFP bidding process, which I don't think works well for bleeding edge technology deployments. You think you can rely on a contract to save you, it will not save you. It's too late by that stage. So contract's going to save no one, and most governments are not going to sue anyone anyway. So, it's much better to avoid that situation by designing it properly in the first place. We do have a large in-house technology team. This co-design does need engineers. Okay, so we have a large engineering team, and that engineering team provides in-house system design, implementation, and support capability. So you do have to pay for that engineering team, but it does give large payback in terms of providing you the capability to have a best fit between science need and technology deployed. It allows you to have strong value for money and agility and first mover status. And of course, if you do this correctly, it lowers risk. And as a result of this, we do have a large focus on technology innovation with our long-standing partners in Intel, NVIDIA, Mellanox, and a UK SME called Stack HPC. I think Stig's talking later. And actually, Stack HPC are involved in probably one of our largest development activities, which is this move away from traditional static HPC systems to a kind of a modern software-defined supercomputer using cloud-native technologies, where you can kind of enable a DevOps or ResOps way of working. You can use hybrid infrastructure, and on top of that infrastructure, you can deploy software-defined research platforms. This is a big shift. And again, we've really pioneered this shift in the UK with Stack HPC. I'll talk a little bit about that. And I think Stig will probably do that subject, much more value than I will in my talk. So I'll just allude to it and allow Stig to talk more detailed about that. So what does our infrastructure look like in the UK? In Cambridge? So currently we have around £27 million of capital equipment in operation. None of that equipment is more than 3 or 4 years old. We have quite a fast turnaround of equipment. 75% of that is funded by UK national activities. 25% of that is funded by Cambridge. We have around 25 staff looking after that equipment and our users currently. That will grow to 45 over the next year, funded by the Exascale lab. Our current OPEX is around 3 million. Most of that is staff. We have a 1.8 megawatt water-cooled data center. We're almost at the top of that power threshold. And inside this infrastructure, we run the UK's first 10 petaflop heterogeneous system that's actually in operation. So we've been in operation for that 10 petaflop system for quite some while. And we have over 50 petabytes of storage. We're also ISO certified within our OpenStack system, which does allow us to produce secure tenancies for medical usage. This was actually our driving use case for OpenStack 5 years ago, where we wanted to deploy separate tenant infrastructure for medical data. So this is what service presentation looks like. It's quite a busy slide. I will talk you through this from the bottom up. So let's start with the things we all love on this call, which is hardware. So at the bottom, you will see in the red box on the right is our newest infrastructure that we've just deployed now, which is a large Intel Ice Lake infrastructure and NVIDIA A100s. On the left at the bottom is a slightly older Intel Skylake, Hadoop, and Intel Cascade Lake infrastructure. It's all InfiniBand now, apart from the Skylakes. And yeah, Gilad, you were right. What can I say? It's all InfiniBand now. We had our foray into OPA, and we all know how that ended. So mostly InfiniBand, some OPA, some Ethernet. Therefore, we do have quite a complex routing infrastructure to route all that data to a single storage infrastructure. Yeah, so all the storage servers are InfiniBand, and then we use Lustre routers to connect that traffic together. And obviously, you want to drive out variation in those routers because it doesn't end well if you have a really complex routing network there. So we are trying to converge now just down to HDR InfiniBand on everything, which means everything plays nice together. Yeah, so that's quite an important kind of direction to try to keep your networking homogeneous as you can. Of course, over time it's difficult because you add incrementally, and so heterogeneity keeps in. But if you don't have a view of driving that heterogeneity out, it becomes a zoo and it becomes difficult to manage. So anyway, on top of the infrastructure, on top of the hardware, we have an OpenStack middleware layer. All of our infrastructure is controlled by OpenStack. And then, of course, you have some people on top of that. We have some engineering teams. And then, of course, what OpenStack allows us to do is present quite a wide range of user access methodologies. This is the real key and power that we get from the OpenStack middleware. We have a lot of flexibility now in how we make those infrastructure elements available. Okay, so we can just have a bare metal Slurm, one large bare metal Slurm. It would look like a traditional HPC cluster. No one would know the difference. We can subdivide our one bare metal Slurm infrastructure if we want into multiple bare metal Slurm infrastructures, which are customizable. We can have virtualized or Kubernetes mediated infrastructure. We can just have infrastructure as a service, like you might buy from a commercial cloud. We can have, again, software-defined data analytics platforms, which we can build on demand. Obviously, there's a whole range of storage services, visualization services. And again, now we're starting to look at HPC access portals. We're bought heavily into Open on Demand from the US. It's a great software environment for making HPC more accessible to novice users. And of course, on top of that, we have our business development user support services and different service entry points depending on what stakeholders are paying to use the service. So we're going to switch gears now. So this is what HPC looks like. From a national perspective, we're really seeing now this understanding, realization that HPC, AI, data analytics, you really have to look at those capabilities as one. And these capabilities are essential pillars, really, driving the national technology agenda, enabling innovation, prosperity, health, and security. This is pretty well understood now, I think, in the UK and globally, that HPC is a national imperative. Of course, we know the broad range of verticals that HPC is used in: engineering, medicine, automotive. I don't have to list them to this audience. And across those verticals, HPC, AI, data analytics is used for basic research, for product development, and of course for business operations. So really these technologies are ubiquitous, both in government, industry, and academia. And there's actually a very good report that's just come out in the UK, kind of looking at these things. If you Google that title, you see it's just about a month old now. And I think that report does a really good job at highlighting why HPC is important on a national level and what type of things you should think about when deploying HPC at a national level. It's a really well-written report, and I suggest that if people are interested in that kind of thing, you should look at that report. So HPC is important. We all know that, but obviously it's changing. HPC is changing radically and quickly. HPC has changed beyond recognition, really, over the last 10 years. I think it's clear to say now that HPC is an absolute basic tool, for the many, not the few. When I look at the research staff in Cambridge that used HPC 10 years ago, and I compare that to the research staff that use it today, there has been a radical change. Okay, HPC is no longer just about scale. Traditionally, HPC was all about scale, and we were only interested in those large power users, those 5% of users that would consume 80% of my infrastructure, because that's how it used to be. We all know that. It was rarely spoken about, obviously, but that was the reality. Now that's completely changed. Today it's about delivering a broad range of flexible, on-demand research platforms to a much broader and diverse set of users. This long tail of HPC has really arrived. Okay, the bulk of my cycles are now consumed by a wide range of modest users. It was not like that before. And this is great for the industry because it's really opened the floodgates to the type of people that can use our systems. Okay. Another change is, of course, research computing is now the fusion of traditional HPC with AI and data. This data explosion is obviously here. Data from experiments, data from IoT, data from public data sets. So really now you can't talk about HPC without talking about data, without talking about AI. That really is a fusion which we all have to understand and design into our systems. And the cost per unit performance has fallen dramatically. Affordability has skyrocketed. Ease of use has radically improved. Workflows have expanded. And this kind of notion of as-a-service cloud provision models are really out there now. And it's freed the user from this kind of cage of a single monolithic shared service. Yeah, and we're only just starting to see the effects of that. We're going to go through another, I think, revolution in terms of usage and growth in users when this kind of as a service cloud model really starts to kick in, which I think it will rapidly. Okay. So HPC has changed. It's no longer your grandfather's HPC, as I tell my engineers. It is now different. So it's really not a question of if HPC, it's a question of how. How do you build a strong research computing ecosystem that delivers for a broad set of stakeholders, university, government, industry, across a broad range of domains and across a broad range of skill levels? There's many things to think about, okay? National versus local, human capital development versus buying more hardware, the mix of technologies, because technology mix is proliferating, unless you're in the interconnect space where it's contracting, but we can talk about that later. The mix of services delivered. How do you measure good? What KPIs? How do you encourage really the broadest range of users? How do you balance your systems between academic use and commercial? Really, how do you get those technologies into the clinic? I think there's a really strong imperative to project HPC services into clinical medicine. We can have large impacts on patient health outcomes if we deliver HPC resources in a way that clinicians can use within a clinical setting. Related to that is this notion of urgent computing. I'll talk about that later. And of course, how do you fund this and sustain this within your local ecosystem and on a national level? So lots of things to consider. And of course, Cambridge has been grappling with these problems for the last 15 years at a local level, at a regional level, and at a national level. So we're going to shift gears again. Now this is the last shift of gear, and I have 20 minutes left on this discussion. So the Cambridge Open Exascale Lab, as I said at the beginning of the presentation, is an industrially funded activity with a whole range of partners. So the activity is funded by Dell and Intel. We also partner with, obviously, the university, with DIRAC, with UKRI, and with the UKAEA. And really, obviously, we all on this call understand that exascale supercomputers hold much promise in terms of solving some real grand challenge problems. So, this is an important nut to crack. But exascale systems obviously present many problems in terms of energy efficiency, in terms of application scaling, in terms of usability. And then, of course, even once we crack those nuts, exascale is a very elitist thing. There's not many people that can afford a 20 megawatt supercomputer. So how do we proliferate those technologies and make them more broadly applicable? This is really what the Exascale Lab is trying to address. It's a leading academic industrial partnership to look at some of these problems through co-design, where we get a critical mass of experience and infrastructure. We're really focused on open standards technologies and how we can address some of these problems and make those technologies accessible to the wider community. And again, you'll hear me talk about this co-design virtuous circle, where we have, in a single collaboration, HPC users, HPC supply chain, and HPC providers, where we get that kind of critical mass of interchange between those different segments. Okay, so we are user-led, science-led. This is a very important principle within the DIRAC consortium that we are an active member of, that all your systems should be designed to meet a user need, to meet a scientific need. It's easy as a provider sometimes not to do that. I can build a supercomputer that I think is sexy and useful for me. Yeah, that might not be the same as what your high energy physicist wants. Okay, so DIRAC's founding principle is science need should lead the process. Otherwise, you have the tail wagging the dog. Right? And so within that consortium, you have need, you have the means in terms of technology elements, and you have HPC providers that have to fashion that technology into a solution. And that this circle is a key element in the way we work and the way the Exascale lab will work. So the funding is now in place. We have a broad set of research themes. These are defined with reasonably detailed project plans and a program manager that started on Monday to deliver those plans. And a recruitment underway for 20 FTE to come and work in the lab. I think the first 4 or 5 posts are being filled now. And several work streams are already underway. So we'll start to describe some of those work streams now. So there's a number of themes. I've listed them here. Obviously, energy efficiency is a key stream. This use case in terms of urgent computing, how do you make HPC resources available for disaster preparedness type activities? I have a slide on that. We have quite a focus on the Intel One API. We have a center of excellence focused on One API. We have a continuing activity around something we call the scientific OpenStack. This is our work with Stack HPC to create this cloud native research computing environment. We have an activity looking at storage. Obviously, how do you feed the beast? The beast is getting bigger. You need more storage performance. We're looking at obviously tiered storage solutions. How do you combine NVMe with slower technologies? There's a whole range of different architectures and thinking around storage. We have a large activity exploring those different ideas and testing them. Obviously, networks is a key element. So continuing InfiniBand developments, we have a whole host of programs underway with NVIDIA networks and Mellanox around exploiting new and emerging InfiniBand features. InfiniBand, never stands still. It always surprises me when I talk to Gilad about, how quickly those guys are developing new features and new capabilities in InfiniBand. That goes on at a pace. So we need to work with those whilst at the same time looking at other emerging technologies with Ethernet and other more novel future networks. And we have an activity around visualization. I will now briefly go over these topics. Because obviously energy is a major inhibitor, really, for HPC at any scale. Power consumption drives kind of 90% of the cost of the data center. And on large systems, it's 50% of the entire life cycle cost, really, including capital. So, energy is a major cost factor. And of course, politically, it's becoming more of a hot potato. It's difficult to go to your chief executive of your university or your company and say, oh yeah, we know that the rest of the university is trying to drive down its power use, but I want another 6 megawatts, please, for my project. It doesn't really compute. It's going against, you're swimming, upstream if you have to go and ask for lots of power. It's just not where people want to go, even if they could afford it. Okay, so we really have to look at maximizing power efficiency. We've already started to look at this with our GPU and x86 systems in terms of frequency control, energy to solution. There's a lot of really neat things you can do with energy to solution if you control the frequency, because obviously we all know that the power of a system is related to the frequency squared. Right? So it's, if you can turn that frequency down, you can save a lot of power. It's quite striking, actually, the power you can save and the energy to solution savings that you can get by doing that. We're writing this work up currently. Also, of course, we need to look at the powertrain in the data center. and understand how choices in data center design can really affect your overall power profile. And again, you can save a lot of power by different data center design approaches. So urgent computing, I mean, this is really interesting, especially when you are looking at national HPC infrastructure. So obviously the recent COVID pandemic has really highlighted, I think, the need and the usefulness of supercomputing for, real-time modeling of situations, for policy and government decision making. Yeah, it's been known quite widely that this is important. There's been a lot of use cases in the US for disaster response with HPC. That's widely known, but I think the COVID pandemic has really highlighted this need. Okay, but it's not easy because, of course, as soon as you want to start doing this, there's a need for data integration with national systems, data security, real-time results. You don't have to wait in a Slurm queue for 2 days to get your answer back. Yeah, so there's lots of challenges. Traditional HPC systems are not compatible with that requirement. Traditional HPC systems are too inflexible and difficult to integrate into the wider IT environments, especially government IT environments. It's like two immovable objects. You have a government IT infrastructure, which is not really very flexible. You have an HPC system, which is not really very flexible. And those two things are not going to come together very well. The disaster's over. Half your population have died before you get the result back, right? So you need flexibility, you need it quickly. And this is where actually cloud computing methodologies are quite useful here, right? With the cloud models, you can have agility and you can have integration. So again, our OpenStack work will really be looking at how can OpenStack mediated supercomputers help in this use case of urgent computing. I think there's a lot of low-hanging fruit in this area that we can work on. So One API is much more traditional. Obviously, this is a new programming language from Intel that targets heterogeneous systems and eases the task of programming across multiple architectures. We're working with a number of key UK codes that I've listed here and how we can port them to Intel Ponte Vecchio with One API. And that engineering resource that's doing that work will then be made available as a center of excellence driving outreach and training within the UK community. So that's quite an interesting one to watch, and you'll see publications coming out of the group on One API. So I think I've talked enough about this. Actually, I think Stig will talk for longer and talk better about this. This is a very large focus for us in how we move to an OpenStack mediated infrastructure and the wide range of possibilities that OpenStack brings in how you serve infrastructure to users and give users access to infrastructure in the way they want it, not the way I give it to them. Yeah, so this is revolutionary, really, I believe, in the way users will gain access and impact from HPC technologies. I'll leave the rest of that for Stig to go over. So I mentioned a focus on solid state storage. We've been looking at this actually for some time, right back from 2019, when we built a very large NVMe burst buffer technology. So this is a kind of a traditional methodology now where you have your spinning disk, you have your NVMe, and via the Slurm scheduler, you can pre-stage the data on the NVMe, run your calculation, and then move it off afterwards. And that's all been written up into a paper on our GitHub. So if you look on our GitHub down there, you can see the documentation. It's all written, deployed with Ansible. So it's infrastructure as code. So if you have the right hardware, the Ansible scripts will help you deploy, build, and test that infrastructure. And back in 2019, we somehow managed to get the fastest HPC storage in the world, which is actually quite surprising if you look at the cost of our storage solution with the cost of some of the others on that list. It shows you what you can do if you just think smart and do new things. And so we're continuing this work now, exploring different mechanisms. There are obvious issues really with this burst buffer methodology. I'm not sure if it really works that well in a busy environment. Glenn Lockwood talks a lot about this on his blog, and there's some really interesting work that Glenn has done and posts he's done. It looks like burst buffers are problematic. So I think this is not a solved problem. Yes, you can make fast storage and you can get a good position in the top in a benchmark, but that's very different to how you use this in real life. Okay, and this is what we're really looking at now. How do you use this? What methodologies and protocols can you use to make this type of performance available? It's two applications. A benchmark might run fast on it, but my application doesn't. And if my application does, how do I stop the burst buffer getting full? And all I'm doing now is making lots of traffic between my spinning disk and my burst buffer. So this is an ongoing issue and certainly not solved in the industry. And I think it's probably one of the largest inhibitors to exascale computing is the storage. So I've talked a little bit about this kind of our IB, Ethernet, and emerging fabrics work. Obviously, IB continues to dominate the world of HPC, and our friends at Mellanox are never standing still with their development of that technology and how they make that useful to the wider world. So we have quite a busy program of work with Gilad and his team looking at how we can exploit and document existing and emerging features in IB, especially the DPU technology. I'm sure that DK will talk about this. I think, smart NICs or the DPU really promises to revolutionize what we can do with networks. And I think will change the networking paradigm completely. Again, I'm not going to talk a lot about this now. Others will talk about it, but I think DPUs are very far reaching in what they will deliver. We're also actively looking at RDMA Ethernet because for many small clusters, work group, departmental, Ethernet is still an interesting technology. We should be looking at that as industry standards for RDMA and Ethernet. And of course, there are these, left field emerging things that always come along that we should be looking at. What else is out there? What's new? We have obviously, if you work in the HPC environment, I've got a typo there, you should be looking at visualization. Once you've generated the results, how do you understand them? How do you develop a kind of a qualitative understanding from a quantitative result? How do you move from results to understanding? And often that comes through visualizing your data. And as we produce bigger and bigger data sets, we need more powerful visualization environments to help our scientists, our engineers, our medics get insight from their data. And we are building various visualization stacks with both NVIDIA and with Intel. And we're collaborating with a lot of Excalibur projects in the UK and their data sets and how we can visualize them. And just to end, obviously within the UK, there is a notion of a pathway to Exascale. The Exascale in the UK should be deployed sometime soon. And on the way to that sometime soon, we should probably deploy a number of incrementally increasing systems. And the Exascale Lab is involved in some of those ideas and potential funding proposals for early phases in that pathway to Exascale. How do we build out our capability to deploy and use Exascale systems? And that is it. That's me done.
All right. Thank you, Paul. Great presentation as always. Got a couple questions here from Sean. He has two. It says, Paul, with your focus on agility and deployments, could you say if you have any issues with heterogeneity between different processor types and generations?
not really issues. Of course, heterogeneity is designed in to our system by design. We have to be aware of it, of course, and from a hardware driver level. But I think we need to be designing specifically to embrace heterogeneity because it's the way it's going.
And the second question is, do you think the current massive increase in energy costs will limit the expansion of HPC or drive low energy solutions in the future?
Energy costs will blow with the wind. It'll be up one day, down the next. So I think, energy cost increases, I think we will weather. But energy costs in general, as we build larger systems, are going up. And yes, we do have to design more cost-effective, energy-effective solutions. It's just, it's a responsibility we all have to be energy efficient in all walks of life. And supercomputing is no different to anything else. It is an inhibitor, as I discussed. So yeah, we have to drive energy efficiency at every place we can.
Thank you for that. Mark, I see you've unmuted. Do you happen to have a question for Paul or?
Yes, I do. So thanks, Paul. Great talk. I was when you mentioned in passing that you said storage is one of the big challenges. I was just wondering, could you say a little bit about the kind of key challenges in the storage subsystems as we go to these larger systems?
Yeah. So there are many challenges, and I can see Gilad's on the call, so I have to be really careful what I say. So, and we discussed this the other day, Gilad. So obviously now, we have very large compute networks to which we have to stream large amounts of data. Okay, how do we do that? So spinning disk is a problem. Most mortals cannot afford hundreds of petabytes of solid state. The large GOE labs can, and that's how they're doing it now. They're saying, okay, burst buffers are difficult. Let's forget the burst buffer. Let's just spend loads of money on one big NVMe system. Then it's easy. So you can do that, yeah, but not many places can do that. And of course, when you do that, what you're doing is you're creating a wonderful congestion engine, because you're going to be pumping in lots of bandwidth into your network. And so congestion control becomes really important. And again, Gilad and I had a really stimulating talk about this last week and some of the new features that are coming in with the NDR around congestion. Yes, so you solve one problem and you create another. Yeah, and as I say, most HPC centers cannot afford a huge NVMe tier. So how do you then deal with storage tiers? How do you move data around between tiers? What are the policies? What are the protocols? How do you design this? I say there have been a few big systems over the last few years in the US that have started to play with this. There was a very good birds of a feather at SC21 that if you Google on, you'll find a lot of stimulating conversations on this topic and a lot of wide-ranging views. I think there's not a consensus in the industry yet on how we do that. And the only way we will probe this is by large-scale test beds, looking at different approaches undertaken by different large-scale machines, comparing and contrasting and exploring this over the next, I would say, 12 months to 2 years. We should start to see a lot more data points coming in. We've had the first rash of large systems in the US that tried this with various burst buffer scenarios. We see a second round of machines coming out now. I think the time will tell over the next 2 or 3 years on different approaches to this problem.
Thanks, Paul.
Great. I currently don't have any other questions in the queue. Appreciate the talk, Paul. Thank you again.
No problem.